Hello everyone. This presentation will describe a methodology that enables quantum compilers to take into account accuracy parameters using symbolic resource estimation. This is a joint work between APFL and Microsoft. Many companies are working on building the first practical quantum computer, which is poised to provide computational capabilities far beyond the reach of any classical supercomputer. Google has recently claimed to have reached the quantum supremacy milestone using its 53-qubit Sycamore computer. IBM provides cloud access to the first fully integrated universal quantum computer, System 1. IonQ has released a 32-qubit computer with massive quantum volume claims using the ion trap technology. In late September 2020, Honeywell achieved a quantum volume of 128 on a 10-qubit fully connected system. Many software resources are needed to program and operate current and future quantum computing systems. Different quantum programming languages are currently available. Microsoft Q#, which is a standalone quantum programming language developed by Microsoft to facilitate the description of hybrid quantum classical programs. Project Q, which is an open-source Python-embedded domain-specific language. Quipper, which is a language embedded in Haskell that does not depend on a particular model of quantum hardware. Scaffold, SCAFCC, which is a compiler framework based on LLVM. Qiskit, which is an open-source framework for working with noisy quantum computers embedded in Python. And QRE, which estimates the implementation cost of algorithms in different physical technologies. These provide domain-specific languages with the necessary abstractions, libraries, simulators, and cloud access to small-scale quantum computers. None of them has built-in support for handling approximation errors. The sequence diagram illustrates the interaction between a classical controller and a quantum coprocessor. A quantum program consists of classical and quantum instructions. The classical controller compiles a quantum circuit from the high-level specification in the quantum program. The instructions in the compiled quantum circuits are sent to the quantum computer, which executes them on the quantum registers. After executing the circuit, classical measurement results are sent to the controller, which may use them to decide on the quantum instructions to perform next. This is repeated until the classical controller returns the final result of the quantum program. This work focuses on the compilation of quantum circuits, which can introduce approximation errors. Indeed, the compilation process is performed by several decomposition steps, generating intermediate representations at different levels of abstraction. Each decomposition may introduce approximation errors. Generally, such approximation errors can be reduced by increasing the number of instructions. This means increasing the resources required to perform the computation. Unfortunately, such resources are limited in any quantum hardware. We address this problem by proposing a methodology that automatically manages approximation errors and enables the programmer to find the best balance between accuracy and resources. We do so by exploiting symbolic resource estimation. In this slide, we describe the quantum circuit model. Qubits are the computational units of quantum computers and are characterized by their quantum state. A quantum circuit is a way to represent a sequence of quantum operations that modify the state of the system. In a quantum circuit like the one shown, each line represents a qubit. Time flows from left to right, and operations are represented by boxes or symbols placed on top of the qubits they act upon. Operations are also called quantum gates and are represented by unitary matrices. The gates that are used to create a quantum circuit belong to a fixed library. The selected library must be universal, meaning that it can approximate any unitary operation with arbitrary precision. We envision that the approach proposed in this work would be most beneficial for large quantum programs. For this reason, we consider the library that is commonly used by fault-tolerant systems. This is the Clifford plus T universal gate library and contains the control node, C node, the Hadamard gate, and the T gate. In the following discussion, we use the number of T-gates as a measure of the implementation cost of a quantum circuit, as this closely captures the cost in a fault-tolerant setting. Where do these errors come from? We can identify three main sources of errors. Algorithmic errors, which are related to the approximated nature of an algorithm. estimation errors, which are related to the precision chosen to estimate a quantity, for example, using quantum phase estimation, and synthesis errors, which are due to the discrete nature of fault-tolerant instruction sets. We saw that approximation errors arise from various decomposition steps during the compilation of a quantum program. How do such approximation errors compose? Consider we want to decompose the unitary matrix U into gates from a universal library. The unitary is decomposed into a set of smaller unitaries, V1 to Vm, with approximation epsilon U. We bound approximation errors in operator NOR. The number of unitaries M depends on the chosen approximation error. The more gates, the smaller the error. In a second decomposition step, each unitary V is decomposed into the native library with approximation error epsilon I. An upper bound on the total approximation can be found by summing up all these introduced approximation errors, as in the shown expression. For approximation-aware programming, we mean writing a quantum program that does not exceed a desired upper bound on the total approximation. Consider the following quantum circuit, which performs quantum phase estimation. It estimates an eigenvalue of an operator U describing the time evolution under a given Hamiltonian. The program includes the inverse of the quantum Fourier transform QFT. We suppose in this example that such a transform is performed in its approximate version. Using current quantum programming languages, the code description of the quantum phase estimation should take as parameters 5 different approximation errors. Programmers are expected to manually distribute all these approximation parameters in the program. For example, they should pass epsilon QFT and epsilon R QFT to the quantum Fourier transform function, where epsilon R QFT is introduced by decomposing rotation gates into the discrete quantum library. Then, programmers must tune these parameters in order to keep the total error within a certain budget. Tuning the accuracy parameters means taking into account both the total accuracy budget for a given program and its implementation cost in terms of the quantum resources required to perform it. Indeed, it is possible to reduce the approximation by increasing the number of operations. In order to assign the most appropriate values to the accuracy parameters, the programmer must engage in an iterative process. This starts by assigning some initial values. Many of the existing quantum programming languages enable us to perform resource estimation if all the parameters of the programs are known. Using the initialized parameters, is it then possible to execute the program and obtain the total circuit cost and the total approximation? The programmer inspects the result and consequently assigns new values to the parameters. This is done until the desired trade-off between approximation and implementation cost is found. This approach still requires some knowledge about how the errors compose to perform an efficient feedback action. Otherwise, the only choice is to repeat the procedure with many values and select the best assignment. There are evident problems with this approach. The first one is the need to manually distribute all approximation parameters in the program's subroutines. The second one is that the resource estimation is a slow process, as it requires to unroll the program into a circuit representation to count the used resources. To overcome the first problem, we propose the integration of language support for approximation parameters. With language support, programmers need to worry about accuracy parameters only in the subroutines where the corresponding errors are introduced, as shown in this pseudocode for quantum phase estimation. The compiler will take care of extracting all the dependencies between the various parameters. Once we know how to express the accuracy parameters, we can focus on how to optimally tune them. Since we are dealing with a trade-off, the approximation error can be reduced by increasing the number of operations. The proposed methodology allows us to find the assignment of accuracy parameters that guarantees the target approximation errors while aiming to minimize the operation count, or find the assignment of accuracy parameters that yield at most the target operation count while aiming to reduce the approximation error. The compiler generates the constraint and cost functions for the optimization problem using AST transformation directly from the source code of the quantum program. Then, it uses the generated cost and constraint functions as input for the optimization process that returns tuned values for all the approximation parameters. Let's focus on step 1. This figure shows the different decomposition levels of the quantum phase estimation algorithm. The standard QPE requires control time evolution unitaries, CEU, followed by an inverse approximate, QFT. At the next decomposition level, each unitary, including the QFT, is decomposed into rotation gates. These rotations will be fed into rotation synthesis, where εr denotes the target accuracy per rotation. Since errors accumulate at most linearly, an upper bound on the overall approximation error can be computed by adding all the epsilons introduced in the various decomposition steps. The compiler generates a function that expresses the dependency of the total accuracy with respect to all the parameters in the program. In this way, we have already achieved automatic accuracy management, but the resulting code will take substantial time to execute. For example, solving the optimization problem using a two-mode simulated annealing requires evaluating the cost and constraint functions hundreds of times. The generated programs contain all the original code control flow, including many loops. For this reason, the evaluation time will depend on the size of the problem. Instead, we propose to generate T and E as symbolic expressions. As it can be seen in the presented plot, the evaluation runtime will not depend on the size of the program. To achieve symbolic and loop-free expressions, we employ custom compiler optimization passes. Functions extracted using AST transformation will feature many loops, performing simple counter increments and floating point additions. A table in the paper reports all the transformation that the compiler passes perform on the intermediate representation code. For example, transformation 1 checks if there is an addition between a variable v initialized outside the loop and a loop invariant, and if v is not used elsewhere in the loop. If so, it adds to v the multiplication between the constant and the number of iterations of the loop. Algorithm 1 shows the pseudocode of the function that computes the total number of t-gates required for the AQFT algorithm obtained after AST transformation. Since we want to extract a symbolic expression of the variable t-count, we have to get rid of as many loops as possible. The if statement in the inner loop may be hoisted, resulting in the min function in algorithm 2. Then, all the loops are flattened by applying the transformations described in the previous slide. Finally, the code in algorithm 2 is obtained, which shows the closed form expression for the t-count with respect to the algorithm's parameters. We developed our first prototype in LLVM as a proof of concept. The cost and constraint function generation is performed by several steps in this prototype. The AST is modified using a source-to-source transformation to generate the cost and constraint functions. Language support is achieved using compiler annotations and matching declarations of accuracy parameters with a custom type. We implement a clunk tool that has access to the AST and allows us to interface with the source code. The clunk tool outputs C++ files containing the functions to compute the t-count and the total approximation error E. All the implementation details are given in the paper. The prototype includes a custom LLVM loop pass to eliminate loops in the expressions. Finally, this prototype also has a method that navigates the fully optimized IR code and extracts symbolic expressions for the two estimates. The symbolic expressions obtained for Shor's algorithm are shown. Many other symbolic expressions can be found in the paper. In our experiment, we compare the runtime required to evaluate the cost and constraint functions with our symbolic resource estimation method against a non-symbolic approach. The non-symbolic approach corresponds to directly using in the optimization procedure the C++ files obtained after source-to-source transformation. We measure the runtime of performing one evaluation of the T and E functions using accuracy parameters guaranteeing an upper bound on the total approximation equal to 5 times 10 to the power of -3. The plots present different input sizes and, for Shor's algorithm and for our QPE example, featuring approximate QFT. The y-axis reports the sum of the runtimes required for evaluating the constraint and cost functions once. While the non-symbolic approach exhibits a growing runtime as a function of the problem size, our symbolic method shows the expected constant behavior. In particular, the runtime of the non-symbolic approach grows linearly for the QPE example and roughly cubically for our implementation of Shor's algorithm. Therefore, we may conclude that non-symbolic approaches are not suitable for large-scale applications. In conclusion, to the best of our knowledge, we are the first to present a quantum programming framework that provides built-in support for automatic accuracy management. Our methodology automatically selects accuracy parameters such that the overall error is at most equal to a user-specified value while aiming to reduce the quantum resource requirements or vice versa. The methodology can be implemented into any quantum programming language. In the paper, we demonstrate the integration into Q#. This concludes the talk. Thank you for your attention.